This is the second video for the lecture Introduction into PDE, and in this video we present section 1.3, only section 1.3. So it's called Scalar Conservation Laws. In this section we consider this differential equation here. Yeah, so f is a function which goes from the real numbers to the real numbers, and the unknown function u, it's defined on R2 and goes to R. And R2 we parameterize by x and t. So x is a real variable and t is a real variable. And this is the differential equation. Yeah, when here, if we use the chain rule, then we obtain this is derivative of the function f, the real function f in one variable, times the partial derivative of u. So this is our differential equation, and we assume that the function f is smooth, and we will see in this part we will first solve this. Also in this section we will solve this equation, and we will see that there show up some problems in some situations, yeah, with the solution. So, also we later we shall present a method of characteristic in general. We have already seen how the method of characteristic solves the transport equation. Now we present the method of characteristic and solve this scalar conservation laws. But before we do this, we will first explain why this equation is called conservation laws. So what is a conserved quantity? And the claim is that for any interval AB, any compact interval AB, the integral over x of the unknown function u is, in the following sense, a preserved quantity, in the sense that we may calculate the time derivative of this integral as a difference of two values. Okay, let's do this calculation. Also, we calculate this. Of course, we may, since these are continuously differentiable, we may put the derivative inside of the integral. Then we have this equation. Then we use the differential equation. Then we get this equation. Yeah, this plus this is 0. So this term is the same as the negative of this. So we have this equation. And now we use the fundamental theorem of calculus. So then we see we have an integral over an interval of a derivative, and this is of course the difference of the values at the boundary. Because here is a minus, we have with plus sign the value at the lower bound at a, and with a minus the value at b. So why we call this conservation law? Yeah, we will see in the next chapter that there also exists higher dimensional conservation laws. Also when x belongs to Rn, there exist similar differential equations, and they have similar conserved quantities. But what does this mean that it is conserved? Yeah, because the derivative is not 0. It means that the change of this quantity, yeah, this density, it comes from a flux. So everything, in order to change this density, there can only flow something in and out along the boundary, and the boundary of this interval contains only a and b. So this f represents a flux. So the flux through the boundary is this difference. Yeah. So this is the meaning of this conservation law, and we will in general see that there exist similar differential equations in higher dimensions. Now we want to solve. Okay, so how we do this? Yeah, we first solve an ordinary differential equation of this form. Yeah, also this means we have given an ordinary differential equation. Yeah, also we assume here. Yeah, we assume that we have already given a solution. Yeah, and then we derive. Yeah, this is completely similar as in the transport equation. So we assume we have a solution U, and then for the given solution U, we now write down an ordinary, an ODE here of this form. Yeah, with initial value that at 0 this should be just in any number x. X is any real number. Okay, and so this is oh, here's a mistake. This has to be removed because no, sorry, this is correct. So U depends on two variables, yeah, and we insert in the first place x of s, and in the second place we insert s. And then this is a real number, and then we evaluate the derivative of f. Okay, and this gives a real number. So this is really an ODE. Yeah, for given u and f, which is differentiable, this is an ODE. And here we have the initial data of the ODE. Okay, of course, if the regularity assumptions are good enough, then we always have a solution of this ODE. Yeah, and now we calculate the derivative of this function. Yeah? This is again very similar than what we have done in the transport equation. Yeah? Now we define an appropriate chosen function set of s. And now let's calculate the derivative of z. Yeah, okay. This derivative depends at two places of s. So yeah, this function, yeah, the right hand side depends at two places. Yes, it's again a composition of this function set of s. Yeah, set of s, which is given by u of x of s, comma s. And this is a composition. Yeah, first the inner function is that s goes to the pair x of s, comma s, and then we have the function u. Yeah, and then it maps to u of x of s, comma s. So if we want to calculate the derivative of this function, yeah, we again should take the chain rule. Yeah, and the chain rule means if we calculate the derivative, then the Jacobian of the first is just the function x prime of s and 1, and the Jacobian of this function here is the gradient of u, and here s is 1, u of x of s, comma s. Yeah, and sorry, not the gradient, but the derivative with respect to x. Yeah, so dx. Okay. So if we insert, if we now calculate the derivative of the composition, yeah, then this is a vector here, and then we obtain this times this, so we obtain this is equal x prime of s times du of x of s comma s by dx. Sorry, and the second derivative, what is the second derivative? Also here the derivative, this is of course dot, yeah, of x of s comma s. Okay, and here plus 1, so we get plus dot of x of s comma s. And now again now we insert this. Now we insert this is the reason why we have chosen this in this way. So what we get if we insert our differential equation, we get f prime of u of x of s comma s times du of x of s comma s by dx plus u dot of x of s comma s. Okay, and then we insert our differential equation and we see it's again constant. Yeah, so it's completely constant, and now our initial conditions, yeah, is are again, here this has to be replaced by a 0. Yeah, I will correct this soon, of course. The initial condition is that u of x of 0 is u0 of x, yeah, for all real numbers x. Okay, and we have chosen the initial condition in such a way, yeah, that for s equals 0, set of 0, this is of course by definition u of x of 0 and 0, and this is u of x 0, yeah, and this is u0 of x. Okay, so we see that set of s is equal to u0 of x, yeah, for all s, yeah, and as long as the solutions exist. Okay, so now what does this mean? Yeah, this means this is along the whole path constant. Yeah, but now if we now return to this differential equation, yeah, then we see x prime of s is equal to f prime of u of x of s comma s. Yeah, but this is of course f prime of set of s, and this is f prime of u0 of x. So it's constant. It doesn't depend on s. Yeah, so it's constant. So we can easily solve this equation. Yeah. So we can now easily solve this, explicitly solve this, and so this means x of s is just equal s times, at 0 it's x, so we should start with the x plus s times f prime of u0 of x. Okay, so what is the outcome? Yeah, so we obtain this equation. Yeah, or x of t. Yeah, so yeah, if we so this means, yeah, now we call st, yeah, because here this is a t. So this means that u of x plus t times f prime of u0 of x comma t is equal to c u0 of x. This is an implicit equation for u. Yeah, this is an implicit equation implicit equation for the unknown function u. Okay, so we didn't found an explicit solution, but we found an implicit equation. Now let's look more carefully at this. Yeah, how do these lines look like? Yeah, what these lines are. So here we have t and here we have x. Yeah, okay, and we have along all the straight lines. Yeah, so when we have here some point, let's say x1, and then we have this way. This is the equation x is equal to x1 plus t times f prime of u0 of x1. Yeah, and let's see. Here we have another x2. Yeah, and the derivative of this line. Yeah, so the slope is just this number. Yeah, but this number depends, of course, on the initial data here. Now let's assume that we have another later line, and then we have x equal x2 plus t times f prime of a0 of x2. Yeah, then we see at this point, yeah, then two such lines might intersect. Yeah, they might intersect, and along this line we have the condition that u is equal to u0 of x1, and on this line we have u is equal to u0 of x2. Now, of course, if the derivatives, also if the values of f prime at these two functions are different, yeah, then they are different. So these two numbers are different. So we get a contradiction here. Yeah? Here, this is impossible. So, yeah, and such a situation where two such characteristic lines intersect, we call crossing characteristics. Yeah, and they really make problems. Yeah, and in the next section we will treat several possibilities how to overcome this problem. yeah, so this means, yeah, here we have exactly such a situation. When we have two values, x1 and x2, x2 is larger than x1, but the slope of the characteristic line at x2 is lower than the slope of the characteristic line through x1, yeah, then they intersect for positive times. Otherwise, they would intersect for negative times if it's the other way around. Yeah, the only way that they do not intersect on the whole plane is if they are equal. So whenever the function f prime takes different values, yeah, then we might have such a problem. Yeah, and then so. Okay, but at least for positive times, we have here a theorem that we have a theorem which states that we have in some situations a solution. So what is the statement? We assume that this function f is 2 times continuously differentiable and u0 is 1 times continuously differentiable. And we now assume that this expression, we will see in the proof how this shows up, is larger than a negative constant. Yeah? Minus alpha, alpha is non-negative, also a non-negative constant. And this should hold for all x. Yeah? Then we have a unique C1 solution of the initial value problem on this domain. So up to the time t, yeah, then we have no problem. Then up to the time t, up to the time 1 over alpha, where alpha is this non-negative constant, also for alpha equals 0, we have it for all times. Yeah, then we have a unique solution. Yeah, okay, let's see how this proof goes. Yeah. Okay, by our solution, yeah, the question is, do this intersect? Yeah, so is there a time t such that the map x goes to x plus, and then we have f prime of u0 of x is injective? Yeah, for fixed t, yeah, in Klammern, for given t. As long as this is the case, then we know that for such t we don't have crossing of characteristics. Now, what is the tool by which we decide whether a function is injective? Yeah, this is a real function depending on one real variable, clearly monotonicity. So the question is the derivative, has the derivative a definite sign? So let's calculate the derivative. Yeah, and the derivative of this function is of course this expression. Yeah, and so this is how this this expression shows up in the theorem. Sorry, yeah, how this shows up in the theorem. Yeah. Okay. Yeah. Yeah. Also we assume, the condition which we assume is that here, that this derivative is that this expression here, yeah, which is exactly this expression, is larger than minus alpha. And if we have this inequality, yeah, then we of course have then this is larger than minus alpha. Yeah, so since we only consider here non-negative times, yeah, this is larger than this, and this is of course larger than 0, as long as t is as 1 plus t alpha is larger than 0, yeah, so which is equivalent, yeah, of course. 1 plus t alpha larger than 0, this is equivalent, then that t is larger than yeah, this is of course larger than 0 because alpha is positive and t is positive. So this is always, yes, this is always, yeah, there we all don't have any restrictions. So we see this is indeed always positive. Okay, so so this function is injective, yeah, and yeah, also by this property, the derivative, yeah, is it's even larger than 1, yeah, also 1, yeah, yeah, maybe we should just write this is larger than 1. Okay, so this means this derivative has a lower bound by 1. Yeah, and if we have a function, yeah, whose derivative has a lower bound by 1, then of a real function from the interval to the differentiable, then we can conclude that the map x going over to x plus f prime of 0 of x is a C1 diffeomorphism from R to R. Yeah, it's of course injective. And why it's surjective? Yeah, of course, the limit x going to infinity of x plus f prime of u0 of x is infinity, and as well the limit x going to minus infinity of x plus f prime of u0 of x is minus infinity. Yeah, since at 0 we have a definite value, then the derivative is at least 1. So it increases by velocity at least 1. Of course, if we go to infinity, then then it goes to infinity, and if we go to minus infinity, it goes to minus infinity. So we indeed see this is a diffeomorphism, and now we can see one diffeomorphism, and now so this means now we can write down the solution. Yeah? So this map has for any t, for any given t, this map has an inverse mapping, yeah, and if we call this map mapping from x to y, then the inverse mapping goes from y to x, and then just insert the inverse mapping in u0, we get the solution of u. Yeah, so in this way we can really solve this. Yeah, and clearly, since this is linear in t, it's differentiable with respect to t, and then of course also the inverse mapping for fixed t. Yeah, then if we consider this as a map depending on t, it's also differentiable. So indeed, we have a differentiable solution. So this equation really defines a differentiable solution. Yeah, so now finally we consider one particular example, namely Burger's equation. For Burger's equation, f is just 1/2 u square, and then we have this equation. So f prime is just the identity function. So we obtain here this equation. Yeah, and let's see, for Burger's equation, is our condition here fulfilled? Yeah, this is this is just u prime times u0, so it depends of course on the function of u0, and yeah, here we have written again the implicit equation. And now if this is continuously differentiable and monotonic increasing, yeah, then this is C1 diffeomorphism from R to R, and so we obtain a unique solution. More generally, yeah, since if this is larger or equal to minus alpha, then we have a C1 solution on such an interval. Okay, so let's recall what we have seen today. Yeah, we introduced the scalar conservation law. Yeah, we introduced the scalar conservation law. Then we understood what quantity is preserved and in which sense it is preserved. And then we used the method of characteristic to solve this equation. And then we understand this problem of crossing characteristics. Yeah, that for crossing characteristics we really obtain a contradiction. So the solution cannot be extended to the whole domain, and but under some weak assumptions we have a solution. Okay, so yeah, also maybe this was a little bit short for Burger's equation. The second derivative, yeah, for Burger's equation here, this equation, the second derivative, yeah, 1/2 x square 1/2 prime, this is of course x, and 1/2 x square double prime, this is 1. So for this reason, for Burger's equation, this condition here, yeah, this term is 1, so we can neglect it, and we only have this condition here in Burger's equation. Yeah, okay. So in Burger's equation, this the condition is exactly the condition that the derivative of this initial function, which fixes the initial values, obeys this equation. Yeah, and then we have a solution here. Okay, thank you.